Okay. All right. Great.
Okay.
Anyway, uh,
Hey, works off mute.
great.
Yes, thank you.
Okay. So I'm going to say hello. I'm Jerry, W9 November Papa India, and s- sitting here at my radio station with the computer and all that sort of stuff. And I'm supposed to be doing some heavy lifting today about electricity and electronics. So hopefully we can make it as painless as possible. And I don't think you'll even lose any fingers or toes. Uh, since we have some new people in here, uh, I guess we should give a few introductions. I've been a ham radio operator since 1957. Got my license when I was 14. They had a license class lower than the technician. It was called the novice class. And you could only have that for 1 year. Then you had to advance up to either a technician or general. So went up the ladder, played with tube radios and stuff like that, and got in the first transistors. I saw a single sideband come in, and right now I discovered this some of the new digital modes, and I'm playing with that now and talking to a lot of people around the world. So that's pretty much what I got. I have a dream station right now, and we'll get into equipment. I think in about 2 weeks. Uh, and I'll talk about how much money you got, kid. See what kind of station you can put together. All right, my partners in crime, actually, the boss of this operation is Bob N8REL. He's our education chairman, and we have Mike, November 8, Victor Delta Zulu, and he's the go-to guy for emergency communications and public service, stuff like that.
Hope you're all doing well tonight.
Yeah, so that's pretty much where we are. Why don't Bob? Why don't you uh, pick this up? And since I think you've got a better list than I do of the people who are here, and why don't you just give us a little introduction. Why why are you here? Pretty much. We start with Richard, and tell us a little about yourself and. Are you trying to become an honest person now and get off the CB bootleggers? Or, I know we've had a couple of guys like that. We've also had some people who want to get their license so they can set up a station for when the SH hits the fan. And we'll take you guys. We'll take preppers and all that. And as long as you obey the rules while the government is still in charge. Otherwise, they can be pretty nasty. And some people want to race drones. We have a couple of channels that are exclusive to radio amateurs. You have to have a license to operate on those frequencies. So if you're in a big contest, you have a less crowded channel you can use. So, Bob, take it away. Bob?
You're on mute, Bob.
Oh, so yeah, Jerry. Well, you just wanted the people to tell us a little about themselves and why they're in ham radio.
Yeah.
Okay, not me too.
No, but he thinks you have a good list.
Oh, hang on, I do. All right, let's start. You know what? According to my participants list right here, the first name that pops up is Rourke Bear. So, Senor, what brings you to amateur radio?
Well, I used to drive a truck for 15 years, so I was kind of familiar with CBs
Mhm.
and tuning antennas and a few other things, and then that's kind of about it. I quit driving. Well, I still got my license, but for a while. But then a buddy of mine, he's got a ham license, and he suggested GMRS for hunting and stuff. We do a lot of hunting, but it kind of stretches their limits. Like on this one chunk of land, it's pretty hilly, and they just don't go very far. And he suggested this, and so I started looking into this and got a license and got a radio and realized it's a slippery slope. And here I am.
Okay. Excellent. Richard, how about yourself?
Well, I'm
And
part of the
oh, yeah, Richard, how do you pronounce your last name, by the way?
Booza.
Who's up? Okay, cool.
I am part of the Warren CERT team, and there's a few of them that have ham radios, Mike included, and others. So I decided, why not? Mike offered it out to us, and CERT is willing to pay for it and give us a radio if we pass all this good stuff. And so I'm not familiar with any ham stuff or CBEs, but other than a cell phone that I have to carry for work.
Okay, excellent. Ace, you're up. What's up?
Howdy. My name's Ace. I'm into ham radio as it's been something that's kind of been on, pun intended, been on my radar for a minute now. I've been into robotics ever since I was a little kid and just
Oh,
taking apart all sorts of weird tech and putting it back together eventually. Um, I work at a place called Batteries Plus nowadays, which I'm sure a few people know. It's a lot of it's kind of a continuation of Radio Shack, but a little bit more specific nowadays. And so ham radios come up through there. I am a complete novice and amateur when it comes to a lot of the ham radio stuff right now, I will say. So figured the technician class was a good place to start.
okay. Yeah, excellent. Um,
Yeah, you're in a good place, Ace, because one of the first things we're going to talk about is batteries. And I got some pictures of some batteries I pried apart.
Cool. I do that a lot of times. I can count on more than two of my hands the number of times I've accidentally set myself on fire doing that too. So
Okay.
okay. Kim, what brings you to ham radio?
So I volunteer for SCCA Pro Rally, and they're always looking for more radio operators. I worked with a guy last year that was doing it, and he said, "Yeah, go get the class." So here I am.
All right.
Is that winter rally up north?
Yeah, I'm heading up in a couple weeks up to Marquette for the next race.
Okay, great.
Okay. Monica, hello. What brings you to amateur radio?
Hey, I'm Monica. I'm a biology faculty person, and I've always been interested in the physics of radio as like a scientist, but I'm also just interested in learning skills that help communities take care of each other, especially in the event of things not going well. So that's kind of my main. I've been excited to do this for a while. So
Okay.
Great.
Thank you. Philip, how about yourself? What brings you to amateur radio?
I guess I'll just round up the class with I fall into the prepper group, I guess.
All right.
I was in the Army. Even farther back than that, I was in Civil Air Patrol. I'm not sure what they use, but I do remember the radio operators class. We go on encampments, go to Fort Custer, get to run around. But yeah, like I said, I just followed the prepper group, I guess. I got little walkie-talkies for me and my kid, and we just started playing around with the CB. I got a little 7-year-old tech officer I'm trying to bring up.
Okay.
Well,
Yeah, Fort Custer. Yeah, I've been there many times. Earlier in my life, I was in the Michigan National Guard for several years, and so yeah, I'm very familiar with Fort Custer.
Yep,
So,
I went from Civil Air Patrol, and then when I was in the reserve, we did time out there. So I spent a lot of time at Custer.
yeah. Okay, Jerry, that's what we have for now.
Yeah, let me just interject one little thing. Over at Detroit City Airport, there's a Civil Air Patrol building, that is supporting one of our antennas, one of our remote stations for our repeater system. So we got some really exciting stuff going on with the Detroit Board of Education, trying to get them into avionics training. Okay, back to you, Bob.
Actually, we're through the list.
That's
Well, before Jerry gets started in his chapter, I want to just let you guys know I come from a background of no electronics at all. I my career, I started out as a draftsman. I was going to go into body design in the auto industry, and then I all of a sudden made a right turn into IT. Um, but it was a lot of code and Linux administration and database administration, and so almost none of this ham radio stuff that you're learning or that we learned applies. And so when I got into this chapter that Bob's going to go through, as it's always been early in the book, um, someone who, one of the teachers from my class, they talked to me off the ledge. And so I just want to say that to you guys. If you don't have that kind of background and you're like, what have I gotten into? This is way too deep. No, it's not. Okay. Let me just tell you, don't let anything in this class drive you away. Like I say, I did not have the background. This is the technician class. It's the basic level. Then there's general. Then there's amateur extra, which is the highest level. I'm an amateur extra now. So I've gone all the way to the highest level you can, and I'm not the smartest cookie in the stack. So I know you can do it. If you have questions, please ask. If it's after class, if you want to ask questions at the end of class or right when they come up, if you want to take yourself off mute and say, hey, I have a question about that. I don't understand that. Please feel free to ask because we want you to be comfortable. Let us talk you off the ledge. Don't don't go over. We'll make it make sense. And like we said last week that we haven't said, but there's new people in the class. We're not necessarily here to teach you amateur radio. We're here to get you to pass the test. So, there's a lot of things that are amateur radio that you're going to learn, but we're really focusing on is what you need to do to pass the test. So stick with us, hang with us, and have fun along the way.
Yeah,
Go ahead, Jerry. Thanks.
Okay. Okay, we got I just got a text. Received the YouTube for the first class. Need the live Zoom link for today. And let's see. Bob, if I give you a phone number, can you zip the test the Zoom information to that person?
Do you have an email address?
I have a phone number.
Okay.
Yeah, you can
Who
just
is
send it. You can just send that in a text message. It'll work.
Okay.
Okay, area
It's kind of
313.
clunky and ugly, but it'll work.
Okay, area 313-820-3722.
And who is this?
I don't know. I don't know how. It might be one of Carlotta's people because I think she has my cell phone number.
Okay. I'll see
Okay.
what I can do.
All right, thank you. All right. All right. Well, let's get it started. All right, I started off with the grommet here, and after you finish this course, and when you pass your test, I send an email out, uh, what every young ham should know. And I have a different picture. I have a young father reading to his infant son or daughter ham radio for babies. And they must have photoshopped the expression on the kid because boy, does he look bewildered. But we're going to try to get you through this test. It's I've had 9-year-olds kids pass the exam, although it's probably better if they're right around 10 or 11 because by that time, fifth or sixth grade math would be enough to be able to do the formulas and stuff like that, and be able to understand it. We're going to talk about, well, I'm hoping that all of you have your ham radio license manual, the ARRL one. That's one we've standardized on. And I'll go through it a little bit, how it's constructed, because it's got some really good stuff. You can preview answers. You can go back and forth on the questions and stuff like that. And they have every question that the exam is going to ask you. We have, so what is it, 350 some questions. And if you have a good memory and memorize all the questions and answers and pass the exam that way, fine. I don't care. It's what we're saying is that this is just like getting your learner's permit. Once you get the license, then you can start learning about how to be a ham. So that's what we'll do. All right, now let's see. I'll have to stop sharing if I. Okay. Okay, I'm going to need a little help here. I don't see a I don't see all my little buttons to stop sharing and all that sort of stuff. Any idea where they are? Oh, here it is. Stop share. Okay. All right. Um, okay, this is something I put together a few years ago. Uh, some of the technology is just a little outdated, but should give you a pretty good idea. First of all, we're doing this under the auspices of the American Radio Relay League, ARRL, and it established in 1914 and been very active in campaigning for hams, lobbying for Congress for more privileges, more frequencies for us, or trying to keep the government from taking away our frequencies. One of the reasons that we have uh, for being here is to actually experiment to increase our knowledge of the state of the art of radio, and we have gone quite a ways on that. Okay. All right. This is an old campaign that they had. Hello, talking to the world. Amateur radio operators come from all walks of life. You don't have to be a techie to get into this. And actually, it's helped me to, in my career, I got a job as an electronic technician with the Postal Service because of.
Just a second, Jerry. Jerry, we're just seeing a list of files. So I'm not sure what it is you want to share.
Well,
But I'm kind of thinking that's probably not it.
that's not it. That's not it. Let me get back to it then. Share. Um, all right, do you see something a little different now? Amateur radio operators come from all walks of life.
Much
Yes.
better. Yep, got it.
Okay. All right. And as I was saying, I got a good career jump because of the stuff I learned as a ham radio operator. Now, we, let's see, at this point, we probably passed 800,000 ham radio operators in the United States.
Radio Kilo 3, Sierra Whiskey Bravo, contest.
The guy who's doing
Mike
a contest
0, Mike
up a
Charlie
mountaintop.
X-ray. And 0, MCX, good morning.
And Japan, Malaysia, young persons all over. And let's see, I said we have about 800,000 hams in the United States, about 2.5 to 3 million in the rest of the world, a lot of Japanese stations. And we usually have 6 or 7 ham radio operators in orbit in the International Space Station.
Out of curiosity, do you know what country has like the most ham radio operators per capita?
Us.
Cool. I was just curious.
Although I think Japan is a very close second. And I don't know, the Chinese have different licensing and all that. We see a few, but we don't. But I think they have some internal channels that they go through. But with the new technology, it's easier and easier to talk to distant countries. So anyway, one of the things that we do is, I think I was describing it before, we have put an antenna on top of a school building. And as the International Space Station comes over the building, we have about a dozen kids talk to the astronaut. And that's something that's really good and encourages STEM studies and things of that sort.
It
And
was
our
one of
company
the, I
has
was
done
part of that team. It was one of the coolest things I've ever done in my life.
Yeah, it is. It is. Okay. Another campaign that ARRL had was license plate bracket. When all else fails, amateur radio works. And one of the reasons why is coming up. Where we come from, bunch of people taking their exams. The FCC, as Bob said last week, is the regulator for everything we do in the United States. The FCC, the United States, is part of a worldwide organization that meets every few years, and they talk about different regulations, different frequencies, different technologies, and things of that sort. But even if the rest of the world does something, we have to wait for the FCC to say it's okay for us to do it. All right, old copy of my license. The licenses go for 10 years. They are renewable, and unless you've done something really naughty, they won't ask you to retest or anything of that sort. They keep going back and forth on charging. At this point, for a new license, you have to pay $35 to the FCC to get the license. If you're under 18, the ARRL has a reimbursement program. We do have, well, with the exams that we give, the FCC has sort of subcontracted to us volunteers to do the dirty work, running the exams and scoring and all that sort of stuff. We do have a $15 charge. If you're under 18, I think it's $5, but there's a charge for taking the exam. But we'll get to that once you get to the exam sessions. A lot of exams are done online, and we still have in-person testing in Oak Park. Okay, argument. Cell phones are better. What, 2013, the Boston Marathon, where a couple of lowlifes set off bombs. One thing that happened was the authorities shut down all cell phone service in the area. They were afraid someone was going to dial up another bomb. Luckily, there were ham radio operators all along the course. They were monitoring the progress of the race, uh, getting supplies, more water at certain stations, or actually being in a sag wagon, picking up people who were injured, things of that sort. So they were in place and they were disciplined enough with their emergency training to be able to help the police manage this horrible thing. One other thing, and I suppose it's getting better and better because we have increased capacity, but if something bad happens and a lot of users get on the cell phone at the same time, they can override the system and everything collapses. We can talk directly from handy-talkie to handy-talkie, or we have a station called a repeater. We'll have a lot more on that in later sessions, where your handy-talkie will talk to the repeater stations, usually on a high up area, like the repeater that our club has is on a top of a 10-story building, and it has a range of about 30 miles. So from you to someone else, handy-talkie to handy-talkie might be 1.5 miles, but with the repeater, could be a 60-mile diameter, 30 miles in one way and 30 miles the other way. Okay, another thing, we do that with amateur radio. And I would invite people into my laboratory, which is the universe. As a matter of fact, back in the 1950s, I believe it was, a couple of scientists were very annoyed. Right around the 420 megahertz radio frequency, they found an awful lot of interference, and they didn't know where it was coming from. They used a directional antenna, and they found that it was coming from outside. And that was the beginning of the radio telescope business. And so, Monica, here's a place where you can shine, and you can aim your antennas out there. Now, this is a set of formulas that a fellow named James Clerk Maxwell put together. It seems that back in the early 1800s, things started coming together. Wire was being developed, batteries of some sort were, power supplies were being made, and magnets, electromagnets were being formed. And electromagnet is a very nice thing because with that you can set up automatic switches, relays, and things of that sort. Someone found, well, they were trying to formulate the rules, physical rules of magnetism, physical rules of electricity. And Maxwell found that the rules were the same. So he put on his thinking cap and around 1865 came out with the formulas and found that electricity and magnetism had a common entity, which was the speed of light, which means that electricity and magnetism were the same. We're going to find out about that a little later in the class. Now, using these formulas, a fellow named Heinrich Hertz, German scientist, did a little experiment. He had a piece of metal with a spark gap. He put some electricity through and made a spark. 15 feet away, he had another spark gap, which was not attached to anything. But 15 feet away, if this sparked, that would spark. So somehow or other, energy was being transferred. Now, this is only 15 feet. However, there was a lot work to be done on this. And actually, well, we were talking last time about the measurement of frequency, and we use hertz in honor of hertz. You're going to find that a lot of the terms that we use are honoring some of our scientists. Now, an Italian fellow named Guglielmo Marconi experimented with this. He managed to get the energy to transfer more than 15 feet. He furnished the Italian Navy with some radio equipment, and then he set up a station in Newfoundland using sparks, and he managed to get his spark transmission to jump the Atlantic over to England. And in doing that, he won a Nobel Prize. He invented enough technology to furnish ships, ocean-going ships, and radio stations all over the world. Made him a multimillionaire. And here he is with some of his inventions. The high technology of the time was a tube with iron filings in it. It was called a coherer. And this was attached to an antenna which picked up these energy waves. And you could hook this up to a circuit to ring a bell or make a click or something of that sort. And that was the high technology that allowed you to receive radio signals. So ships had coherers and spark transmitters. Now, this is all happening in the early 1900s, 1901, 1902. By 1906, or no, 1905, Popular Mechanics. Any other boy can easily make one of these for himself. I am 11 years old. Here is one of the first radio amateurs. And went on from there. And now, we experiment. One of the things that is very interesting to us is the fact that our licenses allow us to dip our soldering irons into the radios that we buy. We can make modifications aside from some purity, frequency purity, spectrum purity rules that we have, and power limitations. We can make our own radios. As a matter of fact, people with Raspberry Pis found that they could actually make a handy talkie out of it. So anyway, this is a little transmitter that is built into a tuna fish can. I'm not sure if some of you are old enough to remember those corkscrew type of light bulbs, but they were packed with a bunch of components to make that fluorescent light bulb work. And of course, Ham started tinkering. They pulled out all the parts, and they made radios out of them. Enterprising. Okay, happy birthday. Mylar Party Balloon. A small transmitter was tied to it, along with a GPS. It was launched from Australia, and you can find websites which show all the maps of all the radio stations that were monitoring this thing. And they tracked the balloon as it went across the Pacific. I think this is where some of the trade winds are. So the winds helped it. One day, it blew the balloon all the way back, a couple hundred miles, and then it had to keep on going, and ended up going across the Pacific, South America, Africa, and ended up in Madagascar. And since that time, other people have launched these balloons, and they've gone around the world a couple of times. And of course, a couple were launched and were probably shot down by American fighter jets because they didn't know what they were. Okay, this is the Eagle, which is a home-built satellite, which a fellow I knew and a couple of accomplices at university built out of various parts. They used camera batteries and solar cells for the power supply. This is the antenna, which was made out of a tape measure. And we had some cooperative measures to get these things launched. And this thing was up for about 6 or 8 months. Every time I went to a ham fest or a swap, the guy who invented this thing would run out and take measurements, point an antenna and it record the telemetry, which you just heard, which told what kind of temperature, battery stage, and all that sort of stuff. And it's purely amateur. This is the kind of antenna that he used. Not very sophisticated, just PVC tubing and some wires, and he was able to track it. And at this point, there are there's tracking software which can tell you what is going to pass over you and how to aim your antenna. So that's another hobby you can look at. And of course, Carlotta's in the waiting room. Admit. Okay. All right. Radios we know usually have dials, usually have knobs and all that sort of stuff. But it's getting better and better, fewer and fewer controls, and you can control your radio entirely from your computer. I do that a lot. Got $5,000 or $6,000, you can get one of these guys, or there's some software. One is Ham Radio Deluxe that I use, which will control the radio, also take charge of your logging, and also tell you if there's a rare station that you haven't contacted yet. And you can put the controls on a Kindle or on your desktop or laptop. This is a method of concentrating 20 stations in the space of one voice channel. And this is the kind of software that we're using that I was introduced with. It's called FT8, which I can talk to Fiji, Oceania, just about you name it. I haven't gotten into Antarctica yet, but I think it's just timing. So here is what we can do. And we are glad that you're joining us, and you too can do one of these many things. All right. Before we get into all the technicalities and heavy lifting, do you have any questions? No questions. Well, either you're too awed or you managed to do a good job. All right. Let's see. Okay. Now, I'm going to go into, okay, share again. And, okay. Can everybody see this page with the diagrams?
Yeah.
Okay, good. Right. This is the amateur radio license manual that the ARRL has put together. They've been doing this for, I don't know, 50, 60 years, maybe longer. And it organizes the questions that the FCC is going to ask you on the license exam, gives you the various types of things that you have to know. At the very, very back, let's see, I hope question pool. Yeah, that's what I'm looking for. Um, where is it? Hope I can get there. Okay. No. It has a guide to all of the questions that are going to be asked on the exam. Last week, Bob was talking about what amateur radio is. About the only question we had that's going to be on the exam is the FCC is going to be the sole rule maker and administrator of amateur radio operations in the United States. We also talked a little bit, and we'll get that into a later course, about how you can talk, who you can talk to. Countries have to have a kind of treaty with the United States for U.S. Amateurs to talk to them. Certain countries like Myanmar and North Korea are kind of difficult to be able to operate. And there are certain rules and regulations about call it third-party trafficking, where you could actually send messages for other people. One of the questions I ask, I'll probably ask it again. All right, there's a fellow who wants me to contact North Korea. His brother-in-law is selling stuff to them, some kind of precision switches that they use in their bombs, and he needs the latest prices. He will pay me $500 if I contact him in North Korea and give him the information. And my question is, how many rules am I violating? So, and plenty of them. So it would cost me my license.
Well, is that like 500 cash or? I'm kidding.
Whatever it takes. Maybe he'll up it to $1,000, and yeah, cut. But some things money can't buy.
$1,000 could be a pretty nice repeater, though. Just saying.
Yeah, put it against the $10,000 fine plus $1,000 for every day you operate like that, and it's not as much. Not as much. Okay. All right, we're going to go into talk about fundamentals of electricity and circuits, voltage and current. Let's see how you have to come out and jump back in. Okay. Okay. Where's my potato? Oh, here it is. Okay. Electronics. Well, all right. We talk about electronics. We're talking about electrons. Where's my? Here it is. All right. All right. Monica, as a physicist, you'll probably laugh at this one because
I'm a biologist,
oh,
aspiring physicist.
okay. Anyway, this is a fairly old-fashioned concept of the atom, planetary type of thing. Was it Niels Bohr uh, concocted this particular thing, where in the center of the atom you have a positive charge, call them protons. Sometimes there's stuff called neutrons, which we have no charge. We don't have to worry about those. And on the outside, we have revolving around it electrons, which are negative. So the charge inside and the charge outside balance each other. They're nice and stable. However, there are some elements that are kind of free with their outside electrons, and sometimes the electrons escape. Now, my son, when he was taking his high school physics class, had this little joke. An electron was one atom was saying to another, "Phooey, I just lost an electron." "You did? Are you sure? Are you positive?" "Yes." And of course, it would be positive because the balance is disturbed. Now, the property of the electron to move along that way. Let's see, where's my other thing? Here. Guys, I'm positively charged. I need an electron. The electrons bounce from one to the next to the next. Now, it has to start from someplace. And you see the hand coming out of the bottom of the battery and a hand grabbing the plus part of the battery. Come on, come on. Yeah, you see them. So you have a flow of electrons. That's what they have called the electrons. Now, how do you start a flow of electrons? There are a couple of ways of doing it. Thanks to Maxwell, he really complicated things. Well, let's start with the lowly potato. And what you have are in this experiment, you have two dissimilar metals. Went to the hardware store, they had some copper nails, I guess they use that for gardening, and found a galvanized nail which has zinc in it. And the copper has lots of electrons. Zinc can pick up electrons. And you have this slightly acidic environment which will allow the electrons to flow from one to the other. So you have electrical current. I think some of the teacher stores have these little experiments they'll sell for a few bucks where you can actually power a little transistor radio with enough potatoes. So uh, now here's one important thing that we have to know. This is a schematic diagram, a symbol for battery. This is a symbol for a light bulb, an incandescent light bulb. Now you can see that the electrons will flow if the wire is complete. If it's open, it's an open circuit, nothing's going to happen. So you have to close the switch to let the electrons go through. I have an experiment I'll show you in a couple of minutes that gives you a little more information about that. So now you have different ways of creating this electron flow. First of all, Well, as I said, I took apart some batteries, and
These look like you got really hungry and like started chewing on them.
yes, actually, but no, sort of look like potatoes, don't they? And
Tasty.
okay, you have different chemical plates of different metals on each end. Actually, these are 6 complete cells. So here's the electrolyte, whatever it is, call it potato or whatever it is, and the metals. And each of these little units produces 1.5 volts. That's the electrical potential, the push, and the volt is named after an Italian named Volta. So we have 1.5, 3, 4.5, 6, 7.5. So how many volts is in this battery?
9.
9. Okay. Back in the day when we used tube radios, there were some portable radios that had 67.5 to 125 volts. And they managed to make enough for the cakes and stuff. Okay.
Had somebody bring in a while back a really, really old battery that was 45 volts, about this big. It was for a I want to say it was for a radio, but don't quote me on that. It was years ago. But it was interesting seeing something like that. It wasn't a lithium battery. It wasn't like a new high voltage one. This was an old lead acid one.
Exactly. And
Very strange.
they usually use 2 or 3 different batteries. One battery, very low voltage, to heat up the tubes, because that would start the electron flow in the tubes. And one high voltage one, like that 45, and maybe another one for some of the intermediate circuits for bias, balancing out the tubes. All right. Electrolyte is hydrochloric acid solution, and we're using different kinds of lead compounds. And of course, these things have a tremendous amount of capacity. Most of them are 12 or 24 volts. Although, if you have forklifts or things like that, you've got much higher voltages and much bigger current. Now, when I was talking about short circuits, or no, I didn't, I talked about open circuits. Short circuit, if you put a pipe or a bar or a wrench across the 2 contacts. Let's see, where is he? Like this.
You get a free fireworks show.
Yes. Yeah, free fireworks show, because you have to have some kind of work for the thing to do, some kind of resistance that will use the voltage. Otherwise, I remember when someone brought in the first NiCad battery that I've seen to our radio club, and it looked like a regular battery. He passed it around to people, and some smarty took his keys out and shorted it. And we know he did it because he yelped and dropped it, because it heated up like nobody's business. And with a car battery, you can do welding. This is welding for a little bit before the acid boils out and explodes. So that's something to be very careful about. Okay. And we have different sizes, different types of batteries. And the thing is, we're getting more and more different compounds in those batteries. Ace, do you know those LiFePO4s?
That would be lithium phosphate, lithium iron phosphate.
Yep.
Lipos are pretty common nowadays too. There's a couple other, there's like 5 or 6 main lithium batteries, but those are, I mean, lithium magnesium is also used in some smaller applications, but there's a lot.
Yeah, well, there is a quest to use lighter and lighter materials and higher voltages, higher capacity and amperage. We'll get into the Frenchman named Louis Ampere in a little bit. But
Ah, my
anyway,
friend.
there are so many different kinds of batteries nowadays, so it's kind of hard to keep track. Okay.
I think you got Dean's connectors on there too. On that.
Yeah.
Yeah.
And no, different kinds, just principle the same. Use some kind of an electrolyte. You use a couple of dissimilar metals for the electrons to flow through. Okay, so the pressure that the electrons force is called voltage, and the amount of electrons going through is called current. And the pressure is measured in volts, or potential, I guess they call it too. It's okay. The potential of the electrons, the force the electrons are forcing through, is called voltage, and is measured by a voltmeter. And our Italian friend, and the number of electrons. I think we've got some units we don't use very much, like coulombs, which actually count the number of electrons flowing past a certain point in 1 second. And I use an ammeter to measure the amperes of a current that are flowing through. And as the Borg say, resistance is futile, but there has to be some kind of thing that consumes the electricity. Otherwise, what's the point of having a battery? So you have a light bulb, you have a radio, you have a heater, all those good types of things that gives purpose. Now, yeah, I was dead from electric shock. This poor, I think it was a 3 or 4 year old. I was no, he was 10 years old. I was teaching a class of 10-year-old kids, and I said, "Oh, I have to tell you about the sad story about this 10-year-old." There was a fixture in his enclosure, and I guess he got hungry or wanted to experiment, so zap. We'll talk a little bit about safety later, but usually anything over about 45 to 48 volts, you can get some damage from. And as far as the amount of current going through you, it takes a surprisingly small amount of current to do very great harm. Okay, do we have any questions so far? Okay. We will have, well, we're recording this. This will hopefully tonight be put on the website, the Jerry's W9NPI channel. And let's see now what, stop, share. Okay, let me see what else we've got in here. Okay. Bob, did you let Larry in?
I did. Yep.
Oh, okay. Yeah, I saw him flash by. Okay.
And there's a Dwayne Daniels. I have no idea who that is, but I'll let him in.
Hi, Dwayne. Okay. All right, I'm going to close this and okay, close that. Okay, we will go into a little bit of math. So last week we talked about gigas and megas and on the big end and micros and picos on the small end of measuring units. The there are probably 3 or 4 different questions on math, on converting units and stuff like that. And believe me, you don't have to take your shoes and socks off to figure out the math on this thing. And we'll save you embarrassment. We have 4 dollar store calculators that we'll hand out if you need them. Okay. Now, right. We'll play with this kind of stuff later on. I have maybe in the second session, all the questions answered, because I want to get into the concepts first. And all of this is in the license manual. It references to the questions in the back of the book. There's a blue border on the pages that have the questions. And actually, if you fold over the blue border, which has the answers, you can use that for questions. Otherwise, the ARRL has a website. Once you register, it's free, but it has a website that will create an infinite number of exams for you. And on the various units, it might talk about rules and regulations, or voltage and current, or things of that sort. And our recommendation is to take as many exams as possible. Once you get up to 85% pass rate or better, you're ready for the exam. As I say, we're trying to get you through the exam, through the learner's permit, and then you can start getting stuff. It's a little different when you get the general class license exam, and a lot different when you get the extra class, because extra class license is good course in radio engineering, and it's got some really good stuff, and you should have a little experience as a ham before you try going for it, unless of course, you are a technician or a scientist and know all this stuff already. Okay. Okay, let's see what else I've got here. Oh, okay. Here's something that okay. Okay, so voltage is measured by a voltmeter. A current is measured with an ammeter. Current that goes in one direction, you notice the batteries are polarized, so there's a positive and a negative. If it goes in one direction, it's called direct current. Here's different kinds of direct current. You can turn things on and off, on and off. And if you turn it off, on and off in a certain rhythm, you are actually transmitting in Morse code. Now, we also have electricity that reverses the polarity. Okay, here's a 0 point. Here's positive, here's negative. And it's going like a sine wave. And we'll try to explain exactly why. Batteries and solar cells are polarized. They give you DC voltage and current. And actually, with a solar cell, you get you charge up a battery, then the battery goes through a little converter that changes the direct current into alternating current, so you can use it for house. And the frequency of household AC is 50 or 60 hertz. I think I use 50 50 cycles or 50 hertz in Europe, 60 here. In the early days of hydropower, Niagara Falls, I think they had 25 hertz or 25 cycles. And it's important if you're buying an alarm clock, because putting a 60 cycle clock on 25 cycles is going to ruin your day. All right, let's get to the next. Okay, now this is a simulated wave. You can see it's mechanically driven. And actually, we're using waves like this all the time. By speaking to you, I'm vibrating the vocal cords to make the sounds. And if you put, you probably saw this various science fairs. If you speak into a microphone and they put you on a scope, your sound is going to look something. Your sound waves are going to look something like this. And the higher the frequency, you can see the closer spaced these little waves are. Okay, now okay, next. All right, can people see this thing with a battery and coil?
Mm-hmm.
Okay.
Yes, sir.
All right. All right. So we have to blame our friend Maxwell for this. It seems that we have an electron flow through chemical means, through a battery. However, if I remember, you probably played with this toy when you were a kid. You have a printed face of a guy in a little packet. There's some plastic over it, and inside that package is a bunch of iron filings. And you take a magnet and you distribute the iron filings to give the guy a beard or a hairdo or something like that. And if you lay a magnet on a table, put a piece of paper over it, and sprinkle iron filings. Actually, I bought some iron filings from Amazon, and they sent it to me in a spice bottle, so I have to be very careful that nobody uses it. Anyway, you sprinkle that on, and you find that the magnet has a certain lines of force. The magnetic force actually arranges the sprinkles of iron filings in a pattern. Now, if you have a couple of magnets, well, here's a bar magnet, and here's a little compass, which has a tiny magnet. You can see that the magnet, well, okay, this magnet is north, it's polarized north and south. And the two magnets, north and south, will go together, but two norths will oppose each other. Now let's try this. All right, I have a light bulb. It's attached to a coil of a conductor of copper wire. which can lose electrons. Now, what happens when I bring a magnetic field into this? The magnetic field is knocking electrons around. Oh, sorry. So it's a terribly confusing thing. Now, even worse, if I have these, a magnetic field, I can use a battery to provide the magnetic field. Even without touching, this disturbs the magnetic field enough to induce electricity through here. So, and it's called a transformer effect because they're not touching. Okay, let's okay, even worse. Now you saw that sine wave, the going when I had that chain going. Now what happens? So you have a revolving magnetic field. Lead is alternating like that. And let's see if I can move this thing over. Shucks. Let me see if I can move this thing over. But this now, if you go down to Monroe, Michigan, or to any power plant, you're going to find a motor of some sort with magnets in it that are revolving near a coil. And this is why we have our 60 hertz or 60 cycles per second alternating current, because it's pretty easy to make electricity this way. It's also very easy to transmit electricity this way, because you can take the pressure of electrons, you can, by using a transformer, you can boost up or boost down the voltage. That's why when you go to Monroe to see the electrical plant, you'll see a whole bunch of towers which are supporting 250,000 to up to 1,000,000 volts. And so it's easy to transfer alternating currents and high voltages to different areas. We'll get into the power equations where you use watts, and you can use either a high voltage and low current and convert it down to a lower voltage and higher current. And it's still doing the same kind of work. Okay, any questions on this? All right. Okay. Okay. Now getting back to the book. All right, so we're here so far. Now, circuits. I talked about circuits. Yes, it has to go round and round in a circle. Otherwise, it's doesn't do any work for us. ARRL likes to use water pumps and compare them to batteries. So we put a voltmeter across the source of the voltage, like right across the battery, and you measure how many volts, how much pressure there is. The voltmeter is sensitive enough and draws so little current that it's not a short circuit. The current meter, or the flow meter, the ammeter, is in series with the flow of the electricity, and it measures the actual amount of current. I don't think it's, well, no, it's using a sort of magnetic way of doing it. It's not counting all the electrons as they flow through. Okay. Okay. And here we have a series and parallel type of circuits. I think they probably improved the circuitry. I don't use Christmas lights, but it used to be that you'd have a whole string of Christmas lights, 50 or 60 of them, and if one bulb burnt out, it would create an open circuit and wouldn't allow the current to flow through. That's a series circuit. Now you can see that in a parallel circuit, each of these is across the battery. So if one burns out, it's not going to affect the others. So that's series and parallel. And open circuit breaks a path and doesn't do any work for you. Okay. Now, back in the day, we had meters that used a little magnetic current, a little magnet and a coil of current that would move the needle one way or another to give you the value of the voltage or current or whatever. Nowadays, things are done electronically with a lot more precision. So they would put an ammeter to measure the current and a voltmeter to measure the voltage in the same box with a switch. Sometimes they actually automatically switch. But the thing is, you have to be very careful with what you're measuring, and especially the kind of one of these things. Yeah. Okay, I don't know if, let's see, can anyone see this? This is a multimeter, and it measures voltage, it measures current. It creates a kind of test circuit so you can actually measure resistance. And also another test circuit that measures capacitance, which we'll get into the way of storing electricity. If you're measuring resistance, do not put high voltage through it. Otherwise, it's going to burn out a whole bunch of stuff. As a matter of fact, I think in one of my demonstrations, I did burn out the ohm meter circuit of this thing. So I'm going to have to.
What is considered high voltage for most of these multimeters?
5 or 10 volts. Doesn't take
Like a
much.
car battery is enough to definitely fry them out.
Oh yeah. Oh yeah. So, okay. I even have one meter that's if you put it next to a household socket, it will tell you whether or not it's live or not. It's managed to pick up the magnetic field of the wire. Okay. All right. We haven't talked about capacitors yet. We're going to talk about two classes of components. I showed you, direct current, which uses electrons, and the use of the flow of electrons. And there's another class of components that use magnetics. Like the coils use a magnetic field to create electricity. And a coil can store electricity. And a capacitor, which is another component, will also store electricity, but it'll store electrons, while the coil will store a magnetic field. So each of these are very, very useful. And of course, when we're starting to make complex currents and signals and things of that sort inside your radio, we use both. Okay. Which of the following precautions taken when measuring high voltage with the voltmeter? I can turn on the old geezer part of me, which says, "You guys ain't seen nothing." I had a radio when I was a teenager that I was an Army surplus thing, and I had to build a power supply for it. 1,500 volts. It's probably around 300 milliamps. That's 0.3 amperes. That would definitely ruin your day. Nowadays, most of the radios are built on a 12, well, a car battery, which is a little over 12 volts. I think, 13.8, something like that. And if you get into a high power amplifier or something of that sort, you might see 48 volts in those. So it's not going to ruin your day as much. Okay. Okay. Actually, if you have a harbor freight store near you, they usually have sales on stuff. There's a $7 or $8 meter that will do an awful lot of good stuff for you, and I recommend that. Let's see, do I still have one, or did I burn all those out? Bob, you have one of those?
What is it you're looking for, Jerry?
I'm looking for I'm looking for a Harbor Freight ultra cheap voltmeter in UM.
Oh, you know what? I do have one of those, but I don't. I use my better one when I need it, so I don't use the.
Well,
Oh.
I gifted mine to my son-in-law, so I can't have him trot out from Denver to give it back to me. But no, these things are cheap, and of course, $7 or $8 meter is more easily replaced than something that's much more accurate and much more expensive. Okay,
Oh,
yeah, that's it.
that's it.
Yeah, it's cheap. It does the job.
Yep, less than $10, or it used to be. I don't know if it still is.
And it's accurate enough for your stuff. You don't have to do laboratory measurements with things like that. Okay. All right. Okay, we got about half hour or so. All right. Resistance is futile, say the Borg. And I hear Professor Dr. George Ohm, OHM, also says that because the unit of resistance is named after him. All these good guys in the 1800s, actually, they used there were some international standards. I know that someplace in France they had a stick that was exactly 1 meter long, and that was the one that they calibrated everything else from. And I think they were arguing about how tall a column of mercury you'd have to make 1 ohm of resistance. Now, if you're dealing with automobiles, you're dealing with heavy currents, and you need very heavy wires to go from your battery to your starter, for instance, because the starter is going to uh, pick up a couple of hundred amperes of electricity. Now, wires, thin wires will start heating up a lot because they have much more resistance than a heavier wire. So one of the useful things about these wires is that you can use them to actually you use the resistance of those wires to do some useful things. For instance, your space heaters use some metal that has a lot of resistance. It keeps the electricity from flowing as best it can, and keeping it from stopping it, from keeping it from flowing, it creates a lot of heat. And our up until 20 years ago, our incandescent light bulbs were pretty much built on the same principle. We had these wires that got white hot when they were subjected to our 110 volts, and we use that to create light. It's a whole other thing with the LEDs, light emitting diodes, because what you're doing, you're emitting photons, and I think the physicists are still arguing about what a photon really is. Is it a wave? Is it a particle? What? But anyway, they're useful, and you can measure things, you can predict things, you can design circuits without having to worry too much. All right, so a lot of metals will conduct electricity. Gold and silver are best, but they're pretty expensive, so we use copper and aluminum. Don't use copper and aluminum together because you have chemical reaction, electrolytic reaction between the two. But you can use those as conductors. Other stuff like wood, ceramics, rubber don't allow the electrons to escape as much. So it takes an awful lot of electricity to pierce through.
Arguably, human skin is also pretty resistant too, as long as it's not wet. Human skin won't let you pass much current through it.
I did a death-defying thing with these 11-year-old boys that I was teaching. I had them all hold hands, and I put an ohm meter the kid at one end, and one contact to the kid at one end, the other contact to the kid at the other end. And I showed them that they were actually creating a resistance. The electricity is going through you, which grossed a couple of them out. Right. And I also showed them an experiment, I think was it Top Gear or whatever. Someone went to a laboratory where they put 800,000 volts through a car with a guy sitting in it. That's another thing we don't get into right now, but it's called being inside the car body itself created a shield called a Faraday shield, and the current just went around you. And after they turned off the electricity, he turned on the car and drove away, and no one was hurt. Okay, right. Resistance, we use R or the letter omega, and the ohm meter is like a test circuit using volts and current, where you can calculate the resistance of a piece of gear or a wire or things that are specially made, resistors, which are specially made to resist the flow of electricity. All right, now here's something. When you do go for your exam, you'll get a piece of scrap paper, and as soon as you sit down, it's a closed book test. You can't go in there. But as soon as you sit down, write these two circles down, because it's the easiest way of calculating resistance, current, and voltage, or current, voltage, and power, or wattage. All you have to do is put your thumb over the value that you want. So if you wanted voltage, you put your thumb over the E, which is another symbol for voltage. You take the current times the resistance. If you want the resistance, put your thumb over the R, voltage divided by the current. So that's or if you're a mathematics genius, which I never was, you can use E equals I times R, and just by using algebra, you can flip one of the components over the equal sign and find out whether to divide or multiply. Okay. Questions? All right. Now there are going to be quite a few questions. Now here's the deal. When you're doing the drills, when you're getting the test questions, you're going to get an awful lot of versions of this. What's the resistance if there's a current of 3 amperes when connected to 90 volts? The reason they have so many of these is that we have different versions of the exam. That's so we can sit people down together and give them different tests so they can't copy from each other. So you get different variations of the question. But if you use those diagrams, it's a cinch. So I'm not going through all these things right now. You can either do it on your own, or if we have time tomorrow, next week. Bob has made a bunch of PDF forms that we can use to go through some of the problems. Okay. Okay, electrical power is in watts. And Not sure if that's James Watt from the inventor of the steam engine or some other Watt. The rate at which electrical energy is used. And heaters, ovens, burners, light bulbs usually tell you how many watts it consumes. Okay. All right, components. All right, ability to restore energy in an electric field is a capacitor. Now, a capacitor is actually a fairly simple thing. It's a conductor and an insulator. Well, usually in sheets. So you have a sheet of tin foil and a sheet of wax paper. You roll it up and well, wait, two sheets of metal of tin foil and one sheet of wax paper. You roll it up, and each of those sheets of tin foil is one part of the capacitor. You can use wax paper. You can use all sorts of different components. I know when Marconi was building his high power station, he had, I think it was a 20 foot by 20 foot by 20 foot high room that was filled with metal and glass, using glass as the insulator. And it works pretty good. Some of the, well, last 40, 50 years, capacitors, very, very high capacitors were designed. I know that at school, some kids, mean kids, would charge up the capacitors and then toss them to somebody. And of course, they touch it and zap. Not, I wasn't one of those mean guys, you know. Okay. So a capacitor stores energy in an electric field. An inductor is a coil which stores energy in a magnetic field. Now, let's see. What happens if you attach a battery to a coil? It creates a magnetic field. When you remove the electricity from that circuit, the magnetic field collapses, and as it collapses, it makes the electrons in the coil start to flow. So that's pretty much how it works. And they each have their purposes. When we get into power supplies, we can see how capacitors and inductors can smooth out or modify the flow of current, and especially the flow of alternating current, radio waves, things of that sort. Okay. So what was that? What type of electrical component stores energy in a magnetic field? Storing energy in a magnetic field. Anybody? Is anybody listening?
Conductor?
Yep. Okay. And some years ago, there was a professor of mechanical engineering who just didn't seem to get it until someone explained to him. It's like a flywheel. The flywheel stores energy in motion. Okay.
Take a guess and say electromagnet.
Almost.
I'll take a guess.
Okay. because you're going to have a little boost there once the magnetic field is collapses. Okay, so resistors, capacitors, inductors. All right, so resistors you measure in what? Joules, henries,
Ohms.
ohms, okay. Capacitors, we're uh, we're honoring was it James Faraday, who was a scientist. He also measured the speed of light as well as measuring the capacitance of components. The farad is a very, very large unit. As a matter of fact, it's only in the last 20 years or so that someone has manufactured a usable, a small enough capacitor. I think there are 1 or 2 farad capacitors now, and they take so long to charge up and store electricity, you can almost call them a battery. So we use microfarads, picofarads as a unit of measurement, especially when we get into audio frequencies and radio frequencies. All right, resistors, different sizes for different uses. Something like this has a very large surface, and they'll dissipate heat. Okay, I bet you don't know what this is because they didn't show the other side of this thing. This is a coil of resistive wire, and it's open on the other side. There's an open channel, and this thing taps into it. So what you can do is adjust the resistance by sliding this up or down. The greater the distance, the higher the resistance. Okay. These are capacitors. You've probably seen lots and lots of these. All right, I'll have to bring one or find it in my junk drawer. But when you're getting into radio frequencies, you're going to use such tiny capacitances that you're going to use air as an insulator, and the plates are going to sort of mesh. The circular plates kind of mesh, and there's very small distance between the plates, and that's a variable capacitor, or some people call them egg slicers. Okay, inductors store energy in the magnetic field. Okay, I don't know if people can see this, but this is a plastic form, and it's got a big coil of wire around it. I haven't measured the resistance on this thing, but sometimes they put this in to get rid of kind of spurious radiation. We don't have to get into tube theory. As I mentioned last week, or Bob mentioned last week, what we're doing is giving you information that's a mile wide and an inch deep. You have to know a little bit, just a little bit, about a lot of stuff. Okay, inductors store energy in the magnetic field and measured in henries. Of course, there was a scientist named Henry. And that chart in the last week's lesson, nanohenries, microhenries, millihenries, and henries. If you're doing power supplies, you're going to find millihenries and henries. If you're going to do audio or radio frequencies, millihenries and microhenries. And here are some of the different kinds of coils. These use air as a inductors. This thing is used as a kind of filtering out of, this goes from the power supply to the transistor that you're powering and does not allow the radio frequency to go back into the power supply. This is an interesting thing. It is an inductor, but it's wound around a ferromagnetic form, which actually increases the amount of inductance. You would probably have something 3 times this size to equal the amount of inductance that's amplified by the toroid core. Okay. Oh, okay. Here are different kinds of resistors that are variable. This one, you've probably seen as volume controls. They're called potentiometers. And here's a small model of my egg slicer capacitor. Otherwise, you might have a couple of pieces of metal that are separated by very thin mica. That's a kind of stone as an insulator with a screw that you can adjust the distance between the 2 plates and adjust the capacitance that way. Okay. Transformers. I showed you that in the experiments. The 2 transformers aren't connected, but they share the magnetic fields. And as long as there is a change of polarity going up and down, going to from high to 0 to negative to 0 and all, that's enough to make the magnetic fields change and transfer. One of the good things is that you can boost things, voltages up. I can take 110 volts from the wall and make a coil, make another coil, let's say make a coil with 10 turns of wire, make another coil with 100 turns of wire, and I can take the 110 volts and boost it up to 1100 volts just by changing that kind of ratio. Or go the other direction and take the 110 volts and put it down to 12 volts, which we use in our current radios. Okay. All right, I think we're going to have to talk about impedance and stuff. Impedance is the equivalent of resistance, but we're talking about alternating currents, things, radio frequencies and such. So we'll talk about stuff like that next week. All right, are there any questions at this point? No? Yeah.
Just where did you say that the lecture recording would be?
Jerry's Jerry W9NPI. Just search for that in YouTube and you'll get there.
Can
You'll
you
see
say
a
it
little
again,
picture.
Jerry's what? W9.
N is November, P is Papa, I is in India. And you'll find a picture of a guy lecturing. I
Okay.
was kind of proud of that. I gave a series of lectures to the Antique Wireless Association. So that's my trademark signature. Okay, so that's pretty much it. And W9NPI at Comcast.net. And I'm friendly. I won't bite. If you have a question for me. All right. Bob, why don't you tie the ribbons?
Okay. All right. So that'll be it for the night then, huh?
Yeah, we'll get into the other
Good.
stuff.
Yeah.
Uh,
Good timing. Good timing. Okay.
and radio circuits, there are 3 radio circuits that's that are going to be on the exam, and they're going to ask you what is this? What is that? So as I say, it's a mile wide and an inch deep. Okay, thank you, Ace.
Thank you, everyone.
Thank you.
Dwayne,
Thanks.
welcome to the class. I hope you got something out of it. Go to Jerry's W9NPI channel. You'll find the first lecture too.
Yeah, I'm on it. I'm on it.
Oh, great.
Jerry, Bob, question. Is there a syllabus in terms of the pace that you're taking? So where should we be with respect to the readings?
Should be in chapter 3 right now. Jerry's gone through part of chapter 3 right now. He'll finish up chapter 3 next week.
Okay. And then we move into chapter 4 next
And then,
week
yeah,
or
right
the
into
week.
chapter 4. Mm-hmm.
Okay. So we should be read chapters 1 through 4 by next week. Got it.
Great. Okay, and just email us if you have questions, and we'll be glad to answer. There's a
Sounds
concept.
good. 73.
73.
73.
Okay. And,
Well, I'll go one better. 74.
For,
I was waiting for that.
for those of you that are in the class that don't know what we're talking about,
Uh,
a ham radio phrase we use a lot is 73. It means best wishes.
Yep. That's
okay. All right. Good night, everyone.
Good night.
Good night.